Hello everyone. In this example, we will be looking at static failure theories, specifically the maximum shear stress theory and distortion energy theory. So these are two different failure theories that we can use to predict the failure for static loads. And while one uses shear stresses, the other one uses an equivalent energy or a von Mises stress to calculate the effective stress that acts on component. So what we have here is a more elaborate problem. So you have a simple gear, a countershaft with two external loads acting on it. So as we've done in previous examples, and including your project, you will have to break down the forces because they're acting at an angle, which is also known as the pressure angle in gears. You will have moment diagrams in two planes, forces in two planes, and so on and so forth. So that's basically what the first, I would say, four subsections of this problem says is determine the force, reaction forces, shear forces, bending moment diagrams, and determine bending stress, torsional shear stress, and then plot a Mohr circle and find out the principal stresses and the maximum shear stress. So I'm not going to dwell on the first three parts much. I've already put down the moment diagrams, the sorry, the free body diagrams, the shear diagrams, and the bending moment diagrams. So what we want to really do is this question here. Build upon the bending moment diagrams to determine the minimum factor of safety for yielding. Use both MSST and DET and compare the results. The material is 1018 cold drawn steel. So what we need to do is figure out what the stresses are as a result of the bending moment and the torsional stresses, plot the Mohr circle, and then use those principal stresses and the maximum shear stress to calculate the factor of safety. So what I'm going to do first is calculate all the stresses I need to plot the Mohr circle. We have the bending moment and we know the torque just looking at the diagram, right? It's going to be some tangential component of one of the forces multiplied by the radius of the respective gear. So let's jump right into that and first calculate the total moment, right? Since we have the moment in two planes, before we calculate the stress, we need to take the sum of squares. So this M total is equal to the sum of squares, and we need to pick which of those 2 points is actually the critical point. So we have a combination of 2033 and 198, and then 2496 and 3249. Like I said, you only have to worry about the peak values in this class. Don't spend any time interpolating between the lines to figure out whether there is a critical point in between the peaks. So it's evident that in this case, it's going to be point B, which is 2496 and 3249. And that makes sense, right? Because you have a smaller gear over there, which is going to require higher loads to provide the same amount of torque. So the higher loads result in higher bending moments. So we have 2496 square plus 3249 square, and that gives us a total bending moment of 4097 Newton meters. Similarly, the torque, right, is going to be some component of let's take the 11,000 Newton force and take the cosine component, 20 degrees, and multiply that by the radius, which gives us 3,101 Newton meters. Again, if you want to do this by yourself, you can pause the video now and go up until drawing the Mohr circle if you'd like, just to see whether you get a hang of these things, and then you can pick up from once I start solving for the failure theories. All right, so once you have the moment and the torque, we can go ahead and calculate the stresses. So we have sigma bending, or in this case, it would be, again, sigma x, right? So we have sigma x is equal to 32m over pi d cubed, because the moment's going to be maximum on the surface. So that's 32 times 4097 over pi times 0.05 cube. So the bending stress is equal to 333.9 Newton meters. And the shear stress is 16T over pi d cubed. So that's 16 times 3,101 over pi times 0.05 cubed. So we have a shear stress of 126.3, again in Newton meters. So now that we have the normal stress and the shear stress, we have no axial load, so we don't have to add anything or subtract anything. We can go ahead and draw the Mohr circle. And I'm going to make a very rough sketch. I'm not going to spend any time calculating the values. I'm just going to plot it and then write down the values. So we have shear axis, normal stress axis, right? And the circle is going to look something like this. That's bad. I'm just going to use a shape here. Yeah, seems reasonable. So we have 333.9 here, and then we have shear axis at 126.3. Similarly here, it would be 0 and negative 126.3, and then I can draw a line across. So this is my center. This is all in megapascals. This is your tau max. This is your sigma 1, and this is your sigma 2. And here sigma 1, if you calculate it correctly, should be 376 megapascals. Sigma 2 is negative 42.4 megapascals, and tau max is equal to the radius, which is 209 megapascals. Okay, this is the center. All right, so these are the values you got. Well done. You have perfected all you need to know about Mohr circle for this class. Again, I only drew a 2D Mohr circle simply because the original circle crosses the shear axis, so I don't need to worry about a possibly larger circle. But if you want, you can draw in the smaller circles in the middle, and it'll be totally fine. All right, so now that we have the Mohr circle and the principal stresses, let's move on to the failure theories. And again, this is static, for static loads. All right, so the first one we're going to look at is the maximum shear stress theory. And what is specific to the maximum shear stress theory, or MSST, as I will refer to it going forward, is it says that the shear yielding strength, SSY, so SY is yield strength in the normal direction, SSY is the yield strength in the shear plane, is equal to exactly half that of the normal yield strength. All right, so this is characteristic of MSST, and it's something you need to remember. It is a conservative estimate, right? Usually we say that the shear yield strength is 0.57 or 0.58 in some books, but for the maximum shear stress theory, which is a conservative theory, when I say conservative, I mean MSST is going to predict failure much earlier than experimental data would show. So that's by reducing the shear strength. And in our case, we have 1018 cold drawn steel. And this is from a different textbook. At the back of the appendix, you can pull out the value. But in our case, here, 1018 cold drawn, this is not available in your textbook. It is 370 megapascals. By now you should, so I think it's in appendices C in the juvenile textbook. You can find you can find material properties, and in this case specifically, we're looking for the yield strength. All right, so SY is in the normal, is the normal yield strength, right? And this is what will be tabulated for the most part. And as SY is going to be your shear yield. So the factor of safety with respect to MSST, actually, let me take a step back. The factor of safety in general is defined as the strength over the stress. And in our case, MSST deals only with shear. So it's going to be the shear strength over the shear stress. So the shear strength in this case is what we've labeled as SSY. And the shear strength, so this is supposed to be tau, not sigma. Over tau max, right? The maximum possible shear stress that this element undergoes in any orientation, which the Morse circle shows us is tau max. And from this equation here, we know that that's actually 0.5 times the yield strength, which we can find at the back of the textbook, divided by tau max. So ultimately, this comes down to the safety factor is equal to the yield strength in the normal direction divided by 2 times tau max. And this is the equation you need to remember for the maximum shear stress theory. This is not in your textbook. So in the exam or in quizzes, if you're asked something about MSST, don't go fishing in the textbook for this equation. It does not exist. Because the only principle of the MSST is that the 0.5 times the yield strength is equal to the shear yield strength. So they would derive any equations. It's something you need to come up with. And you can just write it down. We don't expect you to derive this equation, but understand that this is the equation you need. Now, there's an alternate form to this equation, which is also helpful. So let's look at tau max here, right? Tau max is 2 tau max is basically 2 times the radius of your Morse circle, right? And 2 times the radius is equal to the diameter of your Morse circle. And the diameter is simply sigma 1 minus sigma 2. And this is if you're drawing a 2D Morse circle. If you were to draw a 3D Morse circle, that would be sigma 1 minus sigma 3, because it has to be the diameter of your largest circle because you're dealing with tau max. So you could use the principal stresses or the shear stress from the Morse circle to calculate the factor of safety. So the factor of safety now, if I were to compute it, is 370 megapascals divided by 209, I believe. Yes, 209 megapascals times 2, right, divided by 0.5 basically, is equal to 0.88. So this is NMSST. So this basically means it's going to fail. So the only way to fix this is to either use stronger material or to reduce the load that you're applying to the countershaft gears. Okay. Now, Let's look at the distortion energy method. So we have the distortion energy theory. Right now, what is characteristic of the distortion energy theory? If you've done some SolidWorks before, you would have noticed something called the von Mises stress. And the von Mises stress is basically an equivalent energy based stress that uses both the shear and the normal stresses to give you an equivalent stress. So in your textbook, there are some equations, right? This is in chapter 6 of your textbook, and there are many different stresses that you can use, many different forms of the equation to calculate that von Mises stress. So let me quickly write down the equation first. So N det is equal to the yield strength. You don't need to calculate anything or divide it by 2, nothing. Straight away use the yield strength and divide it by sigma prime or sigma E. I think Juvenal uses sigma E, so we'll stick with that convention. Okay, and what exactly is sigma E? Now, Sy is something you already picked up from the back of the textbook. What about sigma E? Sigma E is an equivalent stress that you need to compute, and it has many different forms. Now, in the event where you have a non-zero principal stress, right, there are possibilities that you'll end up with at least we won't cover that in this class, but there's a possibility that you will end up with 3 non-zero principal stresses, then you can use this equation. In our case, we know the 2 important principal stresses, right, because it's a biaxial stress. You can use this equation, and this is the equation we will use. Now, if you were only to compute sigma, let's say sigma E, and not draw the Mohr circle beforehand, you could just use the stresses that you had. So in our case, we would use this equation, right? We had a planar stress using the bending moment, right? This was with the bending moment. And this was just simply the shear stress in that plane, which was tau, just tau, not tau max, but just tau. Tau max does not show up in the distortion energy equations. This is another form of the equation. If you had, let's say, your critical stress element drawn this way, you had a shear stress, right? And you had a sigma x. This is your tau xy, but you also had a sigma y, right? Then you could use this equation here. So which equation you choose comes down to what you've already solved for. And my advice is, if the question gives you sigma x and tau xy, these values, use those values to calculate your equivalent energy. Because if you try to plot the Mohr circle, and if the numbers go wrong there, and you end up using equation 6.6, then you're going to make more mistakes, right? It's like it's going to propagate and affect your factor of safety as well. However, if you're given the principal stresses, right, and not these stresses here, then use the principal stresses. So try to stick with the values given to you, right? And you won't need to draw the Mohr circle until and unless you need to compute tau max. Now, if you had to calculate both MSST and DET, definitely go for the Mohr circle because you need tau max to calculate the factor of safety for MSST. So that's my spiel about using these equations that are in your textbook. Be familiar where they are, flag them in your textbook with, I don't know, like a tab or some sort of sticky note, whatever works for you. Okay. So like I said, I'm going to use the principal stress-based form of the equation. So we have Sy divided by sigma 1 squared minus sigma 1 times sigma 2 plus sigma 2 the whole square and square root of that. All right, and we already know what those values are. So we have Sy, which is 370. So this one is 376 square minus 376 times negative 42.4. You need to conserve that negative because this negative coupled with this negative shows that your circuit is actually pretty big and crosses the y-axis or the shear axis. So don't forget to include the negative sign there. Plus 42.4 squared, and then take the square root. And once you compute that, you'll end up with the distortion energy theory safety factor as 0.93. And this value is different, and we expect it to be different because both of them use two different methods of trying to solve for the factor of safety. And let me mention that distortion energy theory is actually less conservative than MSST. But distortion energy theory fits, or the failure envelope related to the distortion energy theory fits experimental data much better. And if you're, but again, this will fail as well because it's less than 1, so it'll also fail. Now, one thing to note is MSST is the factor of safety is 0.88, and for distortion energy theory, the factor of safety is 0.93. So